a lot of different innovations and new problems that are solved for people who are suffering from these diseases and different problems affecting their lives. So innovation, as I already mentioned, it creates and solves problems for the future. And many modern day issues that affect different people around the world, such as those living in third world countries and those afflicted by different diseases. Innovation can help solve these problems, and it can help improve the life and the quality of their well-being and improve their daily experiences for both them and their families and those around them. It basically improves the quality of life for those around the world. And so innovation is very important in today's world. So within FTC, how would you innovate? Well, you can innovate in many different ways, but we've outlined here in this seminar today 3 different ways you can innovate. You can use 3D printing, you can manufacture custom parts built specifically for your robot function, and you can also have novel functions for existing parts. Think outside of the box when you use parts that are released at Pitstone or Handymark. You don't have to use the way that they're outlined in the game or how they're outlined in the actual instruction manual. But you can use them in different ways that you've never seen before. And that can all lead to the process of innovation and help break your robots come and become more than what the instruction manual says it can be. So, Sydney, can you hold?
All right, I guess a little intermission. I'm waiting for my son to come up. That's okay. I might as well go ahead and start introducing myself while they're pulling that up. My name is Sydney Young. I am first alumni, pretty much. I was on a team 3525 Xbox a couple of years back, and I've been involved for approximately 8 years total in the first program, and 5 specifically in FTC alone. I've since moved on and gone to Georgia Tech, and I'm currently going to be a second year. And so far, it's been a great experience, and first is definitely a great step towards that kind of stuff. So my role on the team specifically was to be the main CAD designer and the main programmer. So I learned quite a bit about this throughout my experience, so I'm here to share some of that. So I also gave you a quick introduction, but one more thing is of all of the CAD's programs that I've worked with, I've only worked with a couple, and I know that there's things like Autodesk out there and Inventor that are really helpful, but I only know things about SOLIDWORKS for the most part. So if you do plan on thinking about SOLIDWORKS as an option to build parts and build components, I recommend going to my YouTube channel, which if you search SOLIDWORKS FTC Part 1, Part 2, or Part 3, there should be a video there that will provide you some basic information. So I'm going to go ahead and start and say when you should and shouldn't use CAD. There's quite a bit of an overlap, and there's little subtleties here and there, but there's like a general guideline to what you would follow. Most obvious would be to create custom parts, especially if you're going to be manufacturing them or 3D printing them yourself. And a CAD design, and if you don't, you're going to have to pay a significant portion to them so that way they can do so for you, which can be quite costly in the long run. So that's the first point. The next one would be that you might want to modify existing parts. Specifically, good reasons why you would do so is if you have a robot that has symmetric qualities where you might need to cut another part the same size. And a good way to go and reference a part is rather than pull out the original one, you could go and create a 3D model of the modified parts. That way you're better accustomed to making each one more accurate as you go back and cut them yourself. Also, CAD is great for testing, which is probably one of the areas that a lot of people don't really expect at first. There are 2 different ways to test in CAD. One is for fit and one is for function. Fit is probably the most common one that I use, where it's essentially planning ahead before going into the build process and essentially testing how you would put together components so that way they fit within dimensions and make sure that they align properly. It does seem kind of basic and you could do it through the build, but it really just simplifies time by, or condenses time by taking out the process of constantly unscrewing things, putting them back together, taking them apart again, putting them back together, only to realize that, oh, you left this out, time to take it apart again. Also, for function, it works, and there are certain like more complicated matters to do so, but the really basic thing about the function, I guess, is to make sure that you can move parts within it, and to make sure that the components themselves might potentially work. There are more complicated methods within the programs themselves to figure that kind of stuff out, but there are like simple ways to just test out basic ideas, because in the end, you do want to do most of your testing in real life because there's only so much simulation to do. But overall, the important thing about using CAD is that you want to use it to aid the design process. Judges like to see CAD used as a tool and a guide to help you create your robot. It's not so much of a use to create the model after you already constructed the robot, because at that point you could have spent your time doing something else, like volunteering or outreach or other things like that, or even improving your robot further. So make sure that if you're going to use CAD, use it to actually create things to help your robot, and not just to make it as a pretty model afterwards saying, look what we made. So that's the basics of when to use and when not to use CAD. Advantages of using computer-aided design is that it tends to be very cost-effective. A lot of times when you don't plan things ahead, you could end up cutting apart multiple bars only to realize that you needed them in different lengths later on, which means you bought another bar, and another bar, and another bar, and that tends to be kind of a problem in the long run because your funds start to run out. By using CAD, you can plan ahead of what design you want to go with, and if you modify something, you can change it there, and essentially all it would cost is however much money you need to help your computer run using electricity. It also can be very time efficient if used in the proper form. It can make the building process faster by condensing the amount of time that build teams can use to take apart and put back together things. One thing that I do recommend though is to have a general plan before starting to do so. That definitely helps. And it also, CAD also is very precise and accurate. It's something that you can send to a machine shop and they will send it back to you exactly as you asked for it, which is a very nice tool to have. Funny enough, the disadvantages of CAD are the same thing as the advantages, just in a slightly different form. It can be very costly, as in specifically in the 3D printed realm, where you might end up making 5, 6 different prototypes, and eventually that's a lot of plastic. It eventually runs out, you have to order more. So at that point, it's better to create one basic prototype and modify it to reduce the amount of cost that you'd use for CAD after using your CAD and 3D printing it. Also, sending parts to manufacturing is pretty expensive as well, so you need to keep that in mind. CAD can also be considered very time consuming, because if you don't have a general idea before, it's difficult later on, and spend tons and tons of hours only to end up with like some mystic mumbo jumbo that you're going to have to scrap anyway. The reason why is because most CAD softwares are on a stack-like basis where one thing is built off of the next foundation. So if you say, oh, I meant to put like that extra hole here, and it shouldn't mess with anything later on, or you need to modify something previously, it can actually mess with everything else once you go back and modify all of those things. And it makes the process even more difficult to deal with because you have to fix all of the bugs that then occur past it, or like the last 20 steps that you did after it. So it's good to go in with a general blueprint and measurements and whatnot before starting that process. Also, CAD can be a little inaccurate, and not necessarily the program itself, but more of human error. People will always make mistakes. I've made tons of mistakes when working in CAD, and so sometimes you will order something from the machine shop and you realize you didn't add those extra holes, or you've actually added way too many holes, or you put them in the wrong location. So you also have to keep that in mind. Also, when you're working with 3D printers, there is room for error. If you have worked with 3D printers, you might know the notorious hole size problem, where usually you set the size and it ends up being slightly smaller than what you added, than what you were expecting. So you also have to keep in mind that there will be inaccuracies in the 3D printing realm. So now it's down to whether you decide to 3D print, mill, or laser cut your part. And this is, keep in mind, this is just for parts in general, not so much for the design process. When you're 3D printing parts, it's a good idea if you don't want to spend too much money. It has a lower strength value than metal, but it can be also very sturdy. You can certainly look at the robot afterwards to see what I mean. It's great for prototypes because it is cheaper than getting machine shop stuff, and it has the fastest turnaround time. And by quick, I mean like 2 or 3 days, because sometimes you can leave big prints on for a long time. It's just convenient because you can just start it and you can pull it off as soon as it's done. The next cheapest option is probably laser cut, and you can only use that for flat metal surfaces. That's a shorter lead time, which is when you send it to the manufacturer, the CAD design, and when you receive it back. So that time tends to be a little shorter than milling. And it also is a lot cheaper than milling, which is kind of nice. But keep in mind it has to be a flat metal surface. Anything else that isn't, like bars and tubes, that has to be milled. It's the most expensive option and has a long lead time, but sometimes you need that accuracy that a 3D printer cannot provide. And that is so mostly for parts that you want to be sturdy and you want to be very precise, I recommend sending that to milling as opposed to 3D printing it yourself. And so to finish this off, here's some basic tips for CAD designing in general. I know I've said a lot of them throughout this, but I think they're very important points. Part creation specifically, I would recommend that you have a general blueprint or outline prior to going in. Now, I'm not saying you need it like completely and perfectly planned out. I'm just saying have a brainstorming session with your teammates and checking on like how big is this thing going to be, where are we going to place these parts, what parts are we planning on using, and essentially having a fairly strong idea of what direction you want to take your creation. Because by having that direction, it allows you to create the steps to reach that point, so that way you won't have to go back and modify things so much. Another thing I recommend is to determine what material you want this part to be made out of. Like I said, you can determine that by how strong you need it to be. If you're going to use plastic, you need to use the fillet tool, and by the fillet tool, you want to essentially make a nice pretty curve for almost all 90-degree angles, because it increases the strength value of these parts and make them less prone to breaking. Again, you can look at the robot specifically to see what I mean if you want to do so afterwards. So moving on to component building. By component building, I mean like assemblies and slightly more complicated structures. Again, you want to have a general idea, brainstorm with your team. It's usually a good idea to consult the team. And then also make sure to gather your 3D components, like each of the individual pieces. Just because in terms of efficiency, it's nicer to have all of your parts there and then construct it, as opposed to, oh, I need to find this part now, run off, grab it, bring it back. You spend quite a few minutes trying to do that. Just in terms of efficiency, it's better to do all of that all at once, so you don't have to take your mind off of the construction process just to go find something. And then the last note is that if the component or the assembly can be duplicated, save it as its own individual assembly. Specifically, like I said, for parts or components that you use more than once, it's really easy. Like, sure, it may be easy to just reconstruct it again, but I can almost guarantee you that it will take even less time to just copy it and paste that whole construction together into it again, and it'll take less time. So that's all I have for now, and if I'm welcome to take any questions at this time, or we can save it for the end. Feel free to let me know. All right. Is there any questions? Or just clap? All right.
Okay, so thank you, Sydney. Is Christian here? Or not yet? Okay, so then Dale, I guess you can come up and talk.
All right, well, I'm Dale Jordan, and I'm a volunteer for ORTOP and have done so for several years. And they asked me to come here because as we've changed over to the new platform, ORTOP needs to rebuild their demo bots, and we need to be conducting some training this year since it is a big transition. One of the things that ORTOP is very keen in is reusing old stuff and minimizing costs. That's always an issue. So as we looked at our inventory of old parts and the like, we realized we didn't have enough old stuff laying around that would let us build the new robots that we wanted to. So we explored some ways, and that kind of led us down the avenue for 3D printing. And we discovered that after doing a little bit of analysis, we could print an entire robot that would be the appropriate size for doing demonstrations and training for about the cost of 2 medium-sized C-channel Tetrix parts. So that becomes a no-brainer. And I'll just go pull the robot out here in a little bit because it's a tiny little guy. And afterwards, if you want to see some of the new hardware, it's all in this robot. Let's see if it'll set right up here. So one of the things we wanted was to basically have a small robot. Those are very handy if you're in a classroom situation, especially if people are writing programs and stuff, and the robot goes berserk. They're not afraid to go grab a robot, something that's a Lego size. Well, this is a little bit larger than a Lego size, but still it's convenient to grab. Certainly not like Batteries in Black's 55-pound monsters. I will also say too that when I started out doing this, I was not a CAD expert. I knew very little about CAD, and I was able to get my hands on a copy of Inventor, so that's what I learned. But I want to echo everything Sydney said. You know, all the things she pointed out that are important, the keys, things to look for, stuff like that. Yes, I pretty much encountered those as I was learning CAD and building the robot. The things she mentioned about coming up with a game plan when you start, well, that's one of the things that we did. We built this robot up in layers, basically. We kind of settled on the drivetrain, being just the motors, the wheels at the bottom, with the battery, something heavy. That's going to be in the bottom layer, and that's never going to change. Then the next layer, which is our gray layer here, was where we're going to put the control electronics. We started out way before we had any notion of the new system. So one of the first modules was an NXT and a motor controller so that we could just get it running and test the base out. It turns out my son is home from summer before he goes off to grad school. He is doing some stuff, and he's got himself a Project Tango tablet and having a great time. So we built another layer and just set it on the base and a mini FTC field, and then he's just playing around with his own environment. So it is a very modular approach. And because the printing doesn't cost very much, if we change our minds later, we'll just go ahead and update the robots because they're going to be done in layers. The first go around of this, we'll probably just have a mechanism that isn't quite complete yet, and we'll have just kids out there running the robots through obstacle courses and picking up objects and the like, and just making a little bit of a fun exercise for them. We hope to have all this stuff running for the air show coming up next week. Yeah, one of the things that are some of the stuff that I found in doing all of this stuff was the fact that it was small and stuff, and we're doing printing. One of the problems, usually if you buy gears off the shelf, we have gears at the bottom of this thing. I don't know how well you can see that, but the motors and stuff to get the compact size, we wanted to put gears in there. But if you look at the Tetrix gears to get the kind of gear ratios you might be interested in, you usually have very big gears, way bigger than we wanted here. But most of these CAD programs, they support gear designs. And so just with a little manipulation, was able to actually compress the gears down to something that would fit in the chassis of the size we wanted. So that was kind of a big plus of having a nice CAD program for all of that. Certainly plastic is not anywhere near as strong as the metal stuff. So anything that's coupling to a shaft and stuff, we went ahead and used the existing Tetrix collars and coupled them into the plastic gears and whatever else we wanted. Make use of those metal components that are handy and just couple them up with the plastic to get the strength you want. Certainly there were things that whenever things didn't fit, you know, we're able to think in 3D terms of like, what do I need to do to position the parts to get all the wire connections and stuff the way I want. Think about the spatial organization of the components rather than how you're going to have to attach them. Because with the 3D printing, chances are pretty good you'll come up with a bracket arrangement of some sort that's going to let you put everything in place. Other special components. In our case, it's maybe not quite as bad for a larger robot, but we still have the wires that are physically the same size as you do in a large robot. So wiring in the chassis this size becomes an interesting challenge. And how to tie them down as you're building the thing up. And I struggled with that for quite a period of time and ended up coming up with my own version of tie downs. It works great. Turns out when I figured it out, it took about 10 minutes in CAD to design it and 5 minutes to print it. So, you know, problem solved. So it's nice that the 3D printing, along with, you know, things you learn in CAD, you can just go any direction that's necessary. You're not confined by standard parts. Also, with the 3D printing, sometimes it's helpful to have movable parts. For example, here where we got the battery in front down low, we want to get it out of there. So just built as one part a hinge, and then used different material. I used like the nylon to make a latch on the back side so I didn't have to worry about it breaking. When it comes to different materials, this is PLA, which is the most common printing material. It's pretty hard, it's very cheap. It's very tolerant to all sorts of things, just errors and stuff in the 3D printer, and you can get prints that look pretty good. But as soon as you move away from that, it starts to get pretty finicky. Nylon is a great example of something that's almost impossible to print with. But when you are able to successfully do that, you've got some pretty nice, very strong parts. Also did that with motor clamps on the bottom. Turns out nylon tends to stretch a little too, so motor clamps weren't the best there. But you basically go out on the web and you can just search around, and this day there's all sorts of new materials coming out. And I run across a material produced by ColorFab. They call it XT. It's kind of a Teflon derivative, and they claim it works very good. So, you know, I just went and bought a roll and let's just see how it works. I haven't extensively tested the motor clamps on that, but so far the motors aren't twisting in the gears. After we have our sessions with little kids driving these robots all day long, we'll find out if they actually hold up. But that's the nice thing, is that if you do need a different characteristic of the material, just doing a web search can yield all sorts of interesting things. And there's so many hobbyists around that are doing all sorts of experiments with various materials and the like, and great ideas that just see what they've got to say. That's probably where I learned most of the tricks that I did today, was just out there spending an afternoon just surfing the web. Anyway, so at this point, we've got robots that are pretty well completed. The hardware, the electronics came in a couple days ago. So within a day, I had the first robot up and running with the new electronics, which was very exciting after several months of tinkering around to actually see it work with the real hardware. This will be around here afterwards. You guys can come up and poke at this thing. So that's where we stand today. Next week's the trial, when we get it out in front of people for the first time, and we'll see how it holds up. So I guess now I'm kind of open to any questions if anybody has any. quiet audience today.
How much time do you think you actually save if you are not using CAD and 3D printing for building something like this?
Time saved, that's a hard question. I was learning CAD while I was doing this, so I didn't save a single minute on this first pass. I think it allowed me to do something. If I were limited to the standard C channel and other building materials out of Tetrix, which Ortop would have probably followed on with, I wouldn't have had a robot that would have been this compact or really in this sort of form factor at all. So I would have been limited in what I could do, whereas go ahead and taking the time for this, I was able to create something that I felt much better about. And time will tell if it was worth the effort or not. But now I feel very confident that if I were to start a new project with what I know about CAD, it would go a lot faster. Would it go faster than just like bolting C channel together or something like that? Probably not. That's one of those areas like, do you use CAD or not? But where you're in a position where you're likely to have to make your own parts, then I think long term it will turn into be a real time saver.
In terms of overall cost, was it cheaper to build the parts?
Okay, I did a rough estimate of the total cost for the filament for a robot this size, and it's all plastic except for the obvious electronics and the axles and stuff like that. It's about $20, and I kind of buy middle of the road material. You can spend a lot of money to get PLA, or you can spend next to nothing, but I'm kind of somewhere in the middle. For a 1 kilogram roll, it's about I spend about 26 bucks. So you will get, if you're going to print it all one color, then you can probably print, I'm thinking, at least probably 2 robots off of that. But then there's some other special material that's a little more expensive. So about $20 to print a robot. Like I say, that's, if you buy 2 medium-sized C channels from Tetrix, you're going to spend that easily.
And are you using some sophisticated 3D printer or?
I used an Ultimaker 2. Last year with the shootout stuff, it was ranked among the best. So I went a little upscale on that, figuring that if it really caught on for me, I'd probably want something that would give me a little better performance than the really low-end printers. But it sells, I think, for around $2,500. Probably still does today. Yeah.
So before you print the parts, did you design the whole framework or the structure of the robots?
No, I'm one of these guys that likes to tinker. So I had an image of what I wanted the overall thing to look like. And I knew that, for example, the base, I wanted to keep that very compressed. And that's where the motors and stuff were going to have to go. So I focused on that and then left everything beyond that. I guess the overall plan was sort of to do a layered approach, which I stayed true to. So the base was the critical thing, because that was going to contain the heavy components and the stuff that I didn't expect to move. And I wanted to leave everything else open so that I could attach in whatever way made sense. And then the electronics modules, again, I was trying to get them to compress into space, so I focused just on that. And it's just growing outwards. So now we're adding a manipulator. Next step will be putting a bunch of sensors and stuff on, which could alter some of this stuff. But again, it's not expensive to reprint another part. And if you're really interested in conserving material, you can buy yourself an extruder and melt your stuff down again. I thought about doing that, but right now I have just a big garbage can full of old parts. Yeah.
Which CAD tool do you use?
Sorry, I can hear you.
Which CAD tool do you use?
Which CAD tool do you use?
Oh, I used Inventor, and the reason I used it was I just had access to that. Basically, my son was home, and he gave me access to his college account. Had I had easy access to some other one, I would have learned it. People have preached to me that SolidWorks is probably the best one out there, and I have no reason not to believe them. But at home, I have a very slow internet connection. And if I were going to go that route, they kind of force you to work off the cloud. And so I was a little hesitant to go there for performance reasons.
Are those open? Are they open software or do you have to buy license?
I believe the three main vendors will give FTC teams free copies of their tools. Is that true, Cindy?
Yeah, there's a whole process that you can go through, but it's pretty easy. Mostly go to their sites, say, hey, we're a robotics team that would love to use your product, and can we use the student version? And then in 2 or 3 days, it'll let you know, and usually it's a yes. So.
Yeah, for me, just being involved here at Ortop, I probably have to go through a little different process, but my guess is I could probably get access to that. Or I'm gonna just buddy up maybe with a team somewhere.
The other thing is you also get access to Autodesk products. If you're a high school student, you can sign up with a high school account as long as you're a valid high school ID that you can go ahead and send to them. They will allow you to go ahead and sign up for Autodesk products. And PTC Creo is of course provided free with your FTC registration, and you can go ahead and get access to that too. So it really depends upon what tool your team prefers and what the expertise level is built up within the team and what's their preference.
I think learning CAD and doing 3D printing, I've sort of been involved with this program for a number of years, and at least at the higher levels, judging and stuff like that. And I should comment on one of the things the judges talked about a few years ago was they treated like bank spots with their 3D printing. They were just the printing gods, because it was not something that a lot of teams did, and they did it very well. So actually it was, some of the stuff they did, I mean, I didn't have any real motivation at that point to do it, but I was sitting after seeing that sort of like, that's really cool to do some of that stuff. And I guess this was my first real opportunity to do something that was any reasonable size. And from a fun standpoint, I got so hooked on doing what I wanted to do that I was willing to spend the hours struggling to learning how to make CAD work to do what I wanted to do. I was just that drawn into doing this whole process. So I just found this just a fun experience, and I sit down, 10, 12, there was a couple of weeks in here, I was spending about 16 hours a day. I get up in the morning, I work, and I go to bed way late at night, and with the 3D printer usually running. So I see some laughing down here, probably some similar experiences.
She loves sleep.
Because they were practicing in my home, so they were printing was going all night, so we had to shut the doors and everything. But the time-wise, the first year, you kind of, when you get the CAD program down, and you got the printer there, and you kind of, like he said, he spent quite a lot of time tinkering around, which is, you have to get to know your machine. So there's a lot of error and trials kind of go beyond that. And after you get to know your printer, and then I think the first year you're gonna spend a lot of time to get to know it, but the second year will be a lot easier because you know exactly. So.
Yeah, that's a real key point of knowing your printer. To be honest, if I give somebody the CAD files for this, I don't know if it would print on their printer. Certainly that's my interface, and getting to know the printer. I've spent hours just watching it print the same thing over and over again. It's mesmerizing. But pretty soon you start learning the characteristics of what's going to make a good print and what isn't. And for some of these now, it's sort of like if I start them off and go to bed, I have to get up in the middle of the night because I know in a couple hours it's going to get to a point, and I'm going to want to tweak parameters. It is just not feed it your stuff and walk away and forget it. You have to kind of monitor that over time. I know last night I fell asleep and I came up, woke up this morning and I had a bad print. So if I'd watched it all night, it probably ran perfectly.
So what kind of problems?
One of the biggest problems for the printer that I've got is after, especially larger objects. Now, I limited the size of this robot so it would print on just one piece on a bed, so I didn't have to have multiple pieces for the main chassis. Is if it's been printing for a while and then it has to do a solid layer, it tends to start underprinting. And there are a number of reasons for that. When it's printing in the lower layers, it's just fine. So that's one of the things I have to look out for. There's other materials and stuff like that that have their own characteristics. And it's just like you start to see it do something a little bit, and you know immediately that you have to do something or it's just going to go bad. And that's comes from just being mesmerized by the printer for hours on end. And new materials, when I try a new material, I swear, I'm glued to that thing the whole time to see what its behavior is like. I never intended to be that way about it. I just wanted it as a tool, and little did I know that I was just going to be sucked in that way.
Are there companies which print for you?
I believe there are. I've heard stories and stuff like that where people just have banks of printers and just take on jobs. I don't know if that's the kind of job I want to be doing. Also, these printers tend to wear out. I think you probably ought to talk to the batteries in black and how many hours they put on theirs. I notice I've got considerably less, and there are things that have already worn out on my printer. Like the filament guide, it had grooves worn in it until it was grabbing filament and then ruining my prints. I've updated the feeder mechanism on it to get better performance, and the list goes on. So you probably ought to talk to, I think the batteries are probably the team that I know anyway that's got the most hours. Maybe Bank Plots would have had more. I don't know how many hours you guys put in.
Well, somebody asked what kind of problem the printer might give you, and I'm not a part of the team, but my wife and mother of the team. And so when my husband calls from work, because he just turned the machine on and asked me to check on it and see what goes wrong and what goes right. So usually some of the problem I've seen was first layer, you have to stick on the base just right. If you don't, the first thread is wrong or first layer is wrong, it's going to be warped, and it ruins the whole thing. So that means you need to immediately stop the machine and start it over. And the other one was like running out of the thread. You have about 16 hours of printer going. You just ran out and you're almost done and you just ran out the thread. And I thought you could continue doing, but you can't because you have, I don't know about your case, you have to start it over because when you put the new thread, it's not the same as consistency, and the sticking part is not the same, so you have to start it with a big new spool of the thread.
And that's actually the big difference between like the $5 ones and the $30 ones is that the cheaper ones tend to be a little bit lower in quality, have kind of air pockets in it that would make it less strong, while the $26 ones tend to be more consistent and be more of a solid plastic and not have as much gunk in it, which makes it a stronger printed build.
So like you say, you have to kind of get to know your machine and what the problem is. It will take quite a lot of trials.
Yeah, certainly you can also buy $60 rolls of filament too.
But I don't think when you get up to a certain point, like $25 to $6, I don't think there's much difference. You just have to find the right one for you, for the machine.
And at that point, it also comes down to materials like Dale said, is like ABS or PLA or something else.
Yeah, certainly when she mentioned like the warping and coming off the glass and getting it to stick, like I tend to use PLA wherever I can because that's the easiest. But even the big prints there, since the bed is not heated to a uniform temperature, the edges will start to curl. And so there are all sorts of tricks you can do. One of the common one is just put a glue stick down on that. And I find that if I don't put the right amount of glue down around the corners on a big print, it will curl up. And you don't see it until it's about halfway through the print, and then it starts curling. And it curls at about the same rate you're printing, and it just never stops. Which is really frustrating, because the print's looking really good, and then all of a sudden it's just, oh no. The flip side of that, depending on the temperature and humidity, I don't know what other factors that are going on around it, but sometimes if I've used glue stick, it's next to impossible to get the print off the glass. So I usually test some things on small prints if I got a variety of things before I go to a big one to decide, okay, today, how much glue do I need to put down? Where do I need to put it down? And that's a big one. And then again, it's different on the different materials that you use. I know the Color Fab XT, which is a big one, says, glue stick was sufficient and all this other stuff. And the very first print that I did with that is a lot. Glue stick is probably going to curl maybe like nylon or something printing out. So I put plenty of glue stick down, and literally the part just peeled off because I couldn't get it loose from the build plate. So you expect to do some experimenting with that. And again, I don't know what all the factors are, but I swear, what I do one day, the behavior is different than I do from another day.
And also the printer is sensitive to the weather and humidity and the conditions, like if you're putting it in a cold garage, okay, right, and if you put it in a interior of the house, there's a vast difference. And so the best thing, as people have said before, is know your printer, know your material, okay, and be prepared to experiment and spend a lot of time to make sure that you exactly know what you have characterized your printer well.
Yeah, like I said, I never intended to get that involved with the printer, but when you start seeing those prints come out and they're pretty close, you just can't walk away anymore. You're hooked. I would expect all your kids to be the same way too.
And the parts are strong enough generally. You have to design them in such a way, like thicker or...
For this case, at least the base, I designed a little thicker than I think I would normally have put something. Our acid test will be when we put kids on it and they're running around the arena, and if they get into really some heavy-duty battle lots, who knows? It could very well crack and break. The whole thing there is, well, if it does, we can just print another one. The other thoughts were that we might want to put bumpers around there with some of the flexible PLA things there. Again, that's fun stuff to work with. It's very hard to work with many printers. I find actually I'm using flexible PLA to hold the foam in here, and I find I get so excited when I kind of come up with the recipe, the temperature, and the speeds, and the orientation of the part on the plate, and everything that works. I just wrote it all down, and I stick to that now because it works. Whereas before I was doing that, I was getting about a 20% success rate at getting something that would work, or even that was workable. And actually, if you look at the ones on here, they're full of flaws because that material is hard to work with. Turns out the printer I've got with the tube that feeds the material down, if it's flexible, it tends to bunch up, and if you're not careful, you can jam things up and end up with a real mess. So again, this goes back to, for every material, you need to learn how your printer works and how to handle it. Turns out to get the flexible material to work, again, searching the web, one guy said he just puts oil on it, mineral oil. And so for the flexible stuff, I just had a paper towel that I put a little oil on. I just pulled the filament off the reel and just wiped it and let it go through, and that made an immense difference. Of course, when you get enough oil built up, it gets down in the head, it kind of stinks, but I was willing to take the smell for a successful print. Yeah?
Yeah, Cindy, what printer did you guys use?
We had a Mendel Max 2.0.
Mendel Max.
They should have a 3.0 now as well, so. And I think it's cheaper and more accurate at this point.
And batteries in black, what are they using? It would just be nice to have teams that we can call if we have, we can get some of the same printers as opposed to everybody experimenting with different printers.
We also use the Ultimaker too, so we have the same one as Dale.
Is Dale?
Yeah.
Okay.
It turns out when I was looking what to buy, I went around talking to various people, and batteries did a pretty good sell job, plus the shootout that showed that pretty well. guess we turn it back over to you guys.
Okay. All right, thank you so much.
All right, let's all give Mr. Jordan a round of applause. All right, now I'd like to invite up Mr. Christian Kineen and the Thunderbots to give to share their experience with CAD and making custom parts.
Thank you. All right. So one question I have is, how many people in the audience is it their first year doing FTC? If you raise your hands. All right. And then those that have done it for a while, you want to raise your hands? Just to gauge a veteran versus rookie audience participation. Okay. You can set it over there. Excuse me. So someone was asking about the different 3D printers. Since we're on that was a recent question, I'll answer that. I have a MakerBot. Replicator 2 is the version I use. Although, looking online, and I purchased it through my school, because I'm a teacher in Washington. So I might go, one of the ones I've actually been looking at is the Ultimate one instead to replace or to get another version. And there's different reasons I can talk about in a little bit. But, so one of the things I guess I was going to start with is, one of the things we try to really work with my team is trying to do a design process. And design process has different steps. And so, if you can see it, you probably can't, but I'll just explain them. They're listed here, like there's 6 steps, and then it shows them again over here, kind of as a flowchart with a question that goes between them. If you want to look at it later, I'll set it down here. But first thing, CAD or 3D printing, it's really important that you decide what kind of strategy you want and how you want to play the game and how you want to try to score or defend or do what is it that you're going to do with the game, because that initially is going to decide what is it that you need to make and how are you going to make it. Then after that, you'll generate some ideas, do some research, develop a solution, which essentially just means choose what you want to do to accomplish your initial goal of what you want to do. Build it, test it, evaluate it, and then at that point in time, usually you end up having to fix something. And then you kind of keep going through. And the very last step is present the solution, which would be essentially at the competition, you're going to do something with your robot and you'll see how well it works. And then most teams, after the first competition, will come back and try to make more changes, and the process just keeps going and around until Worlds is over for most people. If you get that far, you just, generally, there's always something you want to make better. So these are 2 people from my team. It's Mason, who last year was his first year, so he was a rookie last year. And then Serafina, who's our team coach, or I'm the coach, sorry. She's a team captain. And
Who's in charge here?
you're the coach. She's a team captain, so she kind of helps make sure everything runs smoothly and does a lot actually for the team. So you can go ahead and set that down, and then you guys can wander away if you want. Well, actually, I should have been more precise. I'll set it down so we can see it if you want. So there are a lot of choices going into 3D printing. If you can get a 3D printer, that's great. Most teams, when they're rookies, this is going to be your precise, it's a drill motor. But when most teams start off, the first thing most people kind of you got to learn is how to use a hand tool. And then generally a lot of times you can go to the more advanced stuff. The cool thing about the 3D printing is if you can get a 3D model, you really don't even, you can design it and build it and test it kind of more or less all on the computer. And it solves a lot of problems that go wrong with these when you start just drilling holes and realizing stuff don't line up anymore. I'm trying to pull some stuff over here. So last year, we had our robot, which, like I said, we had four people returning, if I remember right. 3 of them were programmers, and the other one was the captain. So, and last year, the person that did most of the building didn't return with the team. So we had all new builders. And the programmers all still wanted to be programmers, and it was hard for them to do the building because they still wanted to program. So more or less we had a rookie building team. So we started off, the important thing I think with the rookie team is to start off with something simple and then see if you can build up from that. Trying to start with a robot like this when you're first starting out is way overwhelming. And I think a robot, which I can show you a picture of. I didn't bring an actual picture. I had some electronic pictures, but maybe we can get them later. But it looked kind of like a Scorpion with the design that we had. It was very low in the front. It had an angled conveyor, and then we were scoring in the 30. And so we wanted to add something that we could lift up and dump it. So since I thought it looked like a Scorpion, I decided to make something that would be like a Stinger that you could flip up and score with. The problem was, on my 3D printer, it couldn't print large enough to fit inside the space that this goes into. I'll scoot this down another way. So it was printing in basically the inside of here, and so the original design I wanted was larger. So I thought, okay, well, I'll squish it down a little bit, and as I did that, now the wiffle balls wouldn't fit into it anymore. So it was kind of a quick way to find out that this design was too small. So then I had to start over again. This probably took, I think, 12 to 14 hours to print this whole thing. So in a lot of ways it wasn't that bad because it actually printed well by itself. The problem is when you print for about 12 hours and it messes up after about the first quarter of an inch, and then it runs for a bunch of time and you're not watching it thinking it's printing, and you go back and there's nothing there. I think that's one of the biggest problems with 3D printers is they can clog up really easy, and when they clog up, they'll just stop printing. And there is I haven't found an easy way to go back and restart a print. So it is kind of nice to keep checking them to make sure that it's that there's not stuff kind of hanging around the nozzle. So if you get a 3D printer, it is important to kind of, like say, try to talk to someone who has one, and you can kind of avoid some of those problems. So I'll put that down there. So I printed that one, and since I couldn't make a full-size one, what I ended up doing was breaking it into 2 parts. And so this would be to go on the back, and so it was to try to catch them off of our conveyor belt, and then it would dump out. And there was a secondary piece that I was going to print to go on the bottom of it that would snap on or glue on. The problem with it was I got it this far, but being a rookie team, there were some other issues with the robot and time constraints that we never actually got far enough to actually put it on. And then we also didn't advance to our state, the Washington State Championship. So then at that point, we were kind of done with our season. So we got it, but it never got put on in time. The other kind of projects, let me see. So this is another one. I also, so a little bit of history about myself. So I started off as an FRC coach and then went into FTC, and I coach the Thunderbots now from Vancouver, Washington. But I still help out our district FRC team, and then there's another team we're from the Evergreen School District in Vancouver, and then there's a FRC team in Camas that I help them with some different stuff. So our FRC team wanted to make a Swerve Drive, which is a all-wheel steering driving robot. And so what I did is I printed all the pieces out so that they could see essentially how is it going to work, and to make sure all the pieces fit in the right spot and that all the components would go together. And from this, they could, kind of prototype it, or basically look at it and see is kind of everything where it's supposed to be, before spending a whole bunch of time doing the CNC or the machining work to make the actual parts out of. Most everything was made out of aluminum from this. I have one part. This is the upper support piece that went on the up above. So the wheels sat. So basically the wheel would sit this way, and then here's the frame. With the FRC robots, the larger ones, they have a weight constraint. They can't weigh more than 120 pounds, which is really hard. So with them, it's really important to try to remove as much weight as possible. But with FTC, luckily we don't have that constraint right now, so it makes it a little bit easier to not have to worry about that quite so much. I got some more stuff down here if you want to look at. There's some different parts that go with the steering mechanism. I also have a part here, kind of going back to the 3D printing part. This is something that printed, like I said, about 1/8 of an inch to 1/4 of an inch, and it failed for some reason. It stopped. So this is what the inside, if you want to see what the inside of the 3D prints, they're hollow, and they, at least with the MakerBot, they have a hexagon shape that goes on the inside, and you can determine the thickness of the hexagonal shape, the thickness of the outer walls, to give it more strength. So this is a fairly thin print because it wasn't structural. It was just kind of a project that one of my students wanted to make, and so we just kind of printed it. Here's another, this is a project, a school project basically, but they designed a car, and it's an air-powered car, so it has a hole in the back, and it basically goes down a track. And, but this kind of shows one of the problems with 3D printing is, I think it'd be really hard for you to probably see this back there, I don't know, but if you look at the side that's on the top up here, it's kind of bowed. It goes a big arc. And what happened was this actually started with the bow down, and one side started to pull up while it was printing. And so what happened was, as it pulled up, the printing would keep kind of going over the top of it. So when it dried or hardened, it hardened with the bottom being round, and then the top was flat because it kept printing flat. So if you want to see an example of kind of, this can be a problem if your part needs to be square and flush all the way down. So there are things you can do to help it stick to the table more. This particular one, I saw it starting to come up, but I knew the project didn't really matter if it was not totally flat, so I just let it print. So the next level, 3D printing for most FTC stuff is actually usually strong enough to do, especially if you make it thicker, you can make it a lot stronger. But if it's a key structural part, it's really difficult to make it out of the 3D printing. At least I found with my 3D printer, I can't get it strong enough to make the structural parts out of it. So I have the luxury of knowing how to run computer-controlled milling machines, which basically takes a drill motor or a motor essentially that has a cutting bit in it, and you use the computer to program it. Just like designing the parts for 3D printing, you just kind of run it through another process where you create code to make a machine that will run and basically follow a pattern that you want it to make. So these are not FTC parts. These are parts that I used to be a CNC operator and programmer. So this is some parts that I made. This one's just kind of an airfoil for a vacuum. But if you know the process you went through to do this, you can make something like this with a little bit more time and a little bit more training, and it actually isn't that much more difficult in my opinion, but it just takes a little bit more time. What we did was, this was part of an FTC robot from a few years ago. We made the base using kind of the Tetrix pattern on the side of it so that we could attach stuff to it, and attach the motors and different parts on the top. And using the CAD program, we were able to put all of the bolt-down holes in precise locations so that the gears would line up with what the motors were. And I had the CAD file I was going to try to show you, but unfortunately I don't have that. If you really want to see it, I can put it on our Google site, or I could email it to you so you could see it a little bit more. But it's a lot stronger and it's a lot more accurate using the computer-controlled milling parts. But you have to have access to the machines. And I'm trying to think of, I think Hillsborough High School has some CNC milling equipment, if I remember correctly, but that's the one, Don Domes, who I think it's at Hillsborough. I toured his facilities, and he has a lot of, they have some 3D printing, and they also had some 3D CNC machines. So there are some schools that you could talk to maybe to make some certain parts for you. I've made some parts for Batters in Black before that they needed for the robot. And if there's something, really it's nice to make, but again, if you're a rookie team, going through this much detail and effort is really not necessary all the time. You can kind of see the same structural design that they have here with their 80-20 bars, or you can just use the Tetrix pieces, or if you have a matrix system, the matrix pieces. They pretty much work the same way. It just gives you the ability to control exactly what your robot's going to look like and do if you can machine it. And when you take a hand drill, it's really hard to get holes to go straight. It's better is if you can use a drill press. That will get you holes more in line and at least straight usually. But you can usually accomplish fairly decent parts that will work pretty good. Let me see here. And these are parts that our team did a couple years ago for with the blocks in the competition from 2 years ago. They had the blocks. So ours had a sweeper that would sweep it into the blocks, and then the blocks would go into here, and it would tip one way or the other. This was, again, it's a design process. We started with, this was just a rough design that we got high school welding class to weld up some pieces for us so that we could see conceptually how it would work. So this was kind of a prototype. And then that went on to some other parts. We also tried to do it with a plasma cutter with steel. The problem was it didn't make a very good clean cut, and it was a lot of deburring to make it so it wasn't so sharp. And the steel was pretty heavy. This is one of our hook hanging devices that in the competition a couple of years ago, you could get a lot of points at the end of the game if you could lift your robot and hang from it. So we started with metal, and then we decided it was kind of heavy and it was harder to use, so then we went back to aluminum. And the aluminum was a lot easier to use. This one here, which actually turned out pretty good, was made mostly in someone's garage. I took it to the shop and I just took a manual mill and cut the slots and cleaned these slots up. They originally took and cut these out with a Dremel and then drilled some holes and bent it to get it to the shape that they wanted. But this was kind of more or less, that was the third step. And then here was another design that we came up with to try to make it thinner and lighter. So we added a hole here. And the purpose for this, we had to make it lighter because the arm that we used to hang with was the arm we were using to score with. And when we made the arm too heavy, it was harder to score. And so our scoring efficiency went down. So we changed it, and like I said, we came up with different models as we were going along to try to make it. And then the other reason, we added this hole in the top because also if you could get both robots to hang, you got 100 points. So we added a hole in the top because a lot of the other teams, if they tried to hang with us, if it was flat, their piece couldn't grab onto the bar. It was made to grab onto the bar also. So they could fit their hook through the middle and grab onto the bar, so we changed it. So, just kind of leads me back to the beginning here in a way. So you want to come up with a design process. And once you initially decide what you want to do and how you want to score points, you're going to design your robot, make it, build it, test it, and then when you go to your first competition, you're going to realize there are things you thought were going to give you points that don't. And generally you'll find some way that you didn't think was going to give any points that actually is a good way to get points. And then you're going to want to change your robot. And it's a process that you want to keep trying to go through, which, again, the 3D printing is really nice because it's quick and easy, more or less. You know, to try to make a part like this in a garage would have taken a lot of work and probably would not have worked very well. But the 3D printer, within about 10 hours, I think is how long that one took, it was all done and I could start attaching it to the robot and testing it and deciding on whether or not that was going to work or whether we needed to start over with something else. But I think more or less that's kind of it. I know Dale answered a lot of questions and it was really hard having to go after Dale because I respect and admire him a lot, and I was like, oh no, I have to go after him. So, is there any questions that came up during my presentation that you're curious about, or if you have anything other different questions, I could answer those. And it's kind of hard to see, so I think, yes ma'am.
So you actually had 3D parts in your robot during competition?
During the actual competition, we had a few 3D parts. We made some, because we had a rookie team, I don't like telling the team what they have to do, so I really want them to be able to figure it out how they want to do it and what they want to do. So since we had all rookie builders, they were basically trying to figure out how to screw and bolt together the Tetris parts, how to attach motors and gears. So I didn't want to mess a little bit, and I'm trying to think, Mason, I'll pick on you, or Serafina. Do you remember The one parts I could pick up was the triangular parts that we used to try to collect the balls. Did we have anything else on the robot that was 3D printed?
Yeah, the rolling goal clamp, or...
Oh yeah, the rolling goal clamp, which I've got part of it. So, I don't know if you can see this, but this was basically the shape of the rolling goal on one side. This was in the back of our robot. So during autonomous, our robot came down essentially kind of backwards, and then it would roll up to the rolling goal. And these, as it pushed the rolling goal, and then once it hit the wall, it would kind of straighten up usually. We actually got pretty good after a while. And then we had a little clamp piece that would come down and hold the rolling goal onto the robot. This was the first one we made, and if you can see it's just basically kind of like an L. The problem was our clamp would come down and there was nothing to hold it, and so it just pushed it to the floor, and then the robot would lift up off the floor and the rolling goal would stay there. So it was not very effective. So we changed it and we added a little shelf underneath it so that as it clamped, it would attach to this. And so it worked really good for autonomous, because before that we couldn't find a way to actually get the rolling goal consistently to end up in the same spot. So that was right. This was kind of one of the big pieces we had. And then, like I said, we were going to add some of these other parts after that. But this next year we'll do a lot more with it because they have a year of experience, and so the figuring out how to attach stuff won't take as much time, in my opinion, anyway. Did that answer your question?
Yes.
Okay. Any other questions? Yes, sir.
So I think at the very beginning you asked which members are coming from, like veteran teams or rookie teams. So our team is this will be their second year. I know the first year we didn't use a 3D printer. So do you think the second year is the best time to start 3D printing, or maybe wait another year for them to start working on the 3D stuff?
I think it is, because unless you're a rookie team that's being mentored by a team that knows a lot, it's a lot. It's a lot just to figure out how to put everything together. Like our first competition, we do the league in Vancouver, and so our first competition is like the weekend before Thanksgiving, and we were all excited that it was actually moving and it was going to be able to drive for our first competition. And at that point in time, I wasn't even trying to think about 3D printing. But like I said, this year I'll definitely push them more. All of our builders were rookies. So we're a veteran team, but all our builders were rookies. And so this is their second year. So this year, the idea of how everything works doesn't need to cloud their mind so much. So I think as a second year team, you could do a lot more with it, because now you know what worked and didn't work last year. So planning for this year, I think is a lot easier to say, hey, we want to do this and we want to do that, and hey, if we would have done this, or if we would have had something to control the balls and hold them better, we would have scored more points. Or, you know, like the batteries in black, their scoring mechanism. You know, if that was all aluminum, it would have been really heavy, which would have been bulky, and it could have strained their motors trying to score, and so they would have been slower scoring. So there are a lot of advantages to trying to do the 3D printing. We had plastic, a lot of plastic on our robot, which I was gonna this is some plastic. It's really kind of actually, this is slippery, so the parts glide across it. So our conveyor belt, this was the bottom, and then essentially we had the Tetrix conveyor flappers on the top, pushing the balls along this. If we would have advanced farther, I would have wanted to replace this with the 3D printing. But again, at the very beginning, all I wanted was a ramp surface that could at least work. So they made this, and it worked. And it worked pretty good. So in the middle of competitions, it was hard to take this out and put something else in there because it's going to change the way it works. Because every time you change something, it usually can make it better, but it can also make it worse without really knowing it, because if it doesn't line up with the conveyor belt anymore, then you got problems. So I think it's good for a second year team. And as a first year team, if you're being mentored, I think you could do 3D printing pretty easily also. Because they could be the ones that tell you, hey, this worked for us, this didn't work for us, or this is something that a 3D printing part would work really well for, and this may not work very well for. There's also watching, another thing I like actually do is, which I'm very thankful for Batteries of Black, because they post the competitions online, is to look at a lot of the competitions. And if you're a rookie team, look at some of the first competitions, like a first league event, and then look at like a state championship. If you look only at the state championship, you sometimes don't see the fact that some of the teams that were winning the state championship at the first league event were barely working and had a bunch of problems, and they fixed them so that eventually they became a good team. And you can see problems that people have and how they overcome them sometimes through different levels of competition. So I like watching the videos online of different competitions. Any other questions? Yes.
Keep asking questions, but
That's fine.
Dale had mentioned that he used like a glue stick to hold stuff down when he 3D printed to keep it from bowing or curling. What do you do?
Actually, one of the, I don't think I brought it out in the car. On the MakerBot, it's really kind of weird Scotch painter's tape. Actually works pretty good for these printers and holding the parts down. The problem I found is my table is nowhere near flat. It slopes really bad towards the outside because it's a plastic table. So I found that there's a setting you can use to turn on what's called a raft, like a lifeboat or raft. And by turning that on, it creates a really thick layer of plastic. The first, it starts off with a really thick layer of plastic underneath. And then, which these have it, what that does is that helps kind of even the playing field again, because like I said, the plastic goes really thick over here and it gets thinner in the middle and it goes thick on the outside. And that seems to help a lot. But other than that, sometimes I just have to restart because it's like, it's not working. And then I'll restart it. And I've tried to play with different things, but the Scotch tape works pretty good. And I usually have it on this, but it was getting all chewed up at the end of the year, so I ripped it off. And end of the school year, because I was printing stuff for the kids. And I ripped it off, and I tried printing some without it just to see how it was doing. And it worked okay, but I do enjoy doing more. But what happens, if you look at the part like from here, it's really big, but it's actually, there's a little round, these are the bearings for the wheel. So there's 1, 2, 3, there's 4 bearings, and then a bevel gear right here. And then the raft goes underneath it, and then kind of goes wider than it. So there's a black part up here that has the raft on it, and then there's a red bevel gear with a tiny bevel gear right here that has the raft on it also still. And that seems to work pretty good for me, as long as the parts are small. And I just kind of guess when it's really big. Any other questions?
That's a good question, but I think my husband said in the CAD he kind of creates extra, like a surface it can kind of create and holds down to the corners.
Okay.
And it's just the very slight layers, and then when he's done taking off, he just cut that part off. It's like extra foot to hold it down.
Okay.
So what she's saying specifically is that like there's a little like extra rim you can put around, and even like just design some blocks on the corners that are attached to it that are easy enough to snip off, but you can like actually use clamps to hold it to keep from curling.
Okay.
But also instead of using Scotch tape, they actually found online this nice slurry that's like a mix, like part water, part Elmer's glue. That like you just put like maybe 2 layers down and it lasts for months. And as soon as like the temperature dips below like 70, it just pops right off nice and easily.
Yeah.
Like it does work better than any tape or glue we've ever used. So it's like 2 to 1 or something.
And then you just brush.
Yeah.
But anyway.
Which is good. There, if you have a 3D, there's a lot of, like I say, there's a lot of resources online you can look at to figure out. Like mine stopped working or was having issues, like it would skip. So I went online and eventually I found out that one of the wires that runs the motors gets pinched, and then the wires start to break. They fatigue after a while and it stops running. So then I had to buy a new wire for it. Or I could have soldered it together, but since I use it for my school, I figured it's easier just to replace the wire than it is to try to solder them together and hope that it doesn't break again. But yeah, does yours have a heated table?
Yeah.
Okay. This one here, the MakerBot, the Replicator 2 uses the PLA plastic, and so the table's not heated. So the other ones, the table heats up the ABS. There's a Replicator 2X, and then there's some newer ones that they do the ABS, and they have a heated table also. But yeah, actually the clamp idea, I hadn't thought about that. That would be a really good idea. So basically, what she was saying is just you take your, like let's say you're gonna make this part on the CAD system, you would make it either an extra ring wider or just a square that kind of came off the sides, and then you could clamp the square down, and then it can't pull up anymore, right? And I use Autodesk Inventor also because that's what the school has. But yeah, it's actually, they changed it. Any school can get an Autodesk Inventor for free if the school wants to, as well as any student, any teacher, and mentor or coach of first teams can also download it for free. It's in there, it's through Autodesk, and if you go to Autodesk and then Inventor, if you search online for a student download or something like that, it will pop up a page that you can download it for free. And it works pretty good. They actually, the newer versions have a CAM system, so you can actually create toolpath to, if you have a CNC machine, to machine it also. I have a few smaller machines at our school, but then I also teach at the community college part-time at night doing CNC machining, so I can machine stuff there as well. But it's nice if you can find someone that can do stuff if you need it. Any other questions? Okay. So yeah, thank you for the opportunity. I'll try to bring my phone. I can show you some of the pictures of the things that I was printing or what they went onto. Later, if you want to stick around, I can show you what that different stuff is. And I guess I will turn the time back over to you guys.
Okay. All right, so that pretty much concludes our seminar. If you have any questions for the experts, I think, do you guys think you can hang around for maybe an extra 15 minutes? All right, so we also have these robots up here, so feel free to come and have a look at some of the things that our experts have shown. And yeah, and hopefully you'll stick around and get to talk to the experts. Oh, also there's water and snacks outside, so you can grab those and then come back in here.